Welcome back to part 2 of Derivatives in Electrical Engineering. This time we're going to take a look at capacitors. We'll start by putting a voltage across the capacitor, and using derivatives we'll look and see what that means for the current through the capacitor. Now we look at a capacitor. A capacitor is a little bit more complex, but it's essentially the same thing. When we put a capacitor in the circuit, a capacitor is essentially, as shown in the symbol, a pair of parallel plates. And as we put charge on the plates, electrons are stored in the capacitor as charge. And again, they build up a voltage between the plates so that the voltage across the capacitor, here as we apply it, will be a 5 times T e to the minus 10t volts. And we're going to make this a 0.1 microfarad capacitor. Most capacitors are measured in microfarads or picofarads, 10 to the minus 6 or 10 to the minus 12. There are much larger capacitors, but in the kind of circuits that are typically electronic circuits, we'll stick with the microfarad or picofarad. So with that voltage applied, what we're looking for is the current through a capacitor. And the definition of the current through a capacitor is equal to the capacitance times the change in voltage across the capacitor with respect to time. So we look at our voltage across the capacitor as 5t e to the minus 10t, and we see a different kind of construction, because now we see that the voltage is equal to one function times a second function of t. In this case, f of t is the 5t. G of t is e to the minus 10t. So now we end up with the question, what do we do with derivative of one function of t times another function of t? So let's look at the product rule for derivatives. Starting with our problem, f of t times g of t is 5t, that's f of t, times e to the minus 10t. The derivative is defined as the first function times the derivative of the second function plus the second function times the derivative of the first function. So if our first function is 5t, its derivative is 5. Our second function is e to the minus 10t, so its derivative is minus 10 e to the minus 10t, using the chain rule that we looked at previously. So our derivative of f of t times g of t is 5e to the minus 10t plus 5t times minus 10e to the minus 10t. Let's put that together, collect terms, and we can isolate out a 5e to the minus 10t, at which point we have as many 1 minus 10t. So that's the derivative of our voltage. Now that we know how to calculate the derivative of the product of two functions, we're ready to put the problem back together again. We start with our derivative of the voltage with respect to time, 5e to the minus 10t, times the quantity 1 minus 10t. We're going to add the value of the capacitor in now. The capacitance is 0.1 microfarads. Well, if 1 microfarad is 1 times 10 to the minus 6, then 0.1 will be 1 times 10 to the minus 7. And we'll put that into our equation, and now we'll collect terms. Rearranging slightly, because our minus 10 here times a minus here will give us a plus. We'll take the 5t e to the minus 10t, multiply that by 10, so 10 to the minus 7 times 10 will be 10 to the minus 6, and the first portion of our answer is here, 5 times 10 to the minus 6 t e to the minus 10t, and then the subtraction still holds for the second term, and that's going to give us a 5 times 10 to the minus 7 e to the minus 10t amps. So there's the current flowing through our capacitor with respect to time. We've looked at the mathematics of the capacitor's voltage and current characteristics. Now let's look at the curves produced by it. Here's the voltage that we're applying across the capacitor. As you can see, it's going to come up and it's going to peak a little after 0.1 seconds. Now this is interesting as we watch the current through the capacitor, because as the instantaneous voltage is coming up, that instantaneous voltage is going to produce a lot of current. But as the curve stabilizes, we see the currents decreasing, and when the current, or when the voltage changes polarity, actually doesn't change polarity, when the voltage stops increasing and starts decreasing again, you notice that we are going to have a change here, because now the change in voltage producing a change, and now the current, as we reach steady state, is going to go to 0 as the steady state voltage applies. So those are the waveforms that describe what's happening. So now you've seen an introduction to the derivatives in electrical engineering. As you can tell, it barely scratches the surface. We looked at a few components, the inductor and the capacitor, but it goes much farther. We can go into signal processing, we could go into instrumentation, we can look at radio frequency transmission, radar, medical imaging. All of these functions include derivatives. So start with the capacitor and the inductor, and I hope you have fun with it.